All right, good morning, afternoon, evening. This is Math 1, Mr. Trutna, Clovis High School. This is Worksheet 5.4G. These are going to be the solutions, and it's involving exponential growth and decay, and a couple problems involving compound interest. Diving right into the assignment in numbers 1 through 4, we're going to identify the initial amount A and the growth factor B in each exponential equation. Okay, so in number 1, we're going to have the initial amount is always going to be the number before the base that has the exponent of x. So my initial amount here in number 1 is going to be 3. And then the growth factor is always going to be the number that is the base of the exponent that is going to be x. So my growth factor is going to be 5. Okay, in number 2 here, my initial amount, which I'm going to refer to as IA for initial amount, is always the number that is before the base that is to the exponent of x. So my initial amount is 250. And then my growth factor, which I'm going to refer to as GF, is always the base of the value that has the exponent of x. So my growth factor is going to be 1.065. Okay? In number 3, you notice that number 3 is missing the first value that we're going to multiply by. So what you have to do is you have to think to yourself, you have to say, okay, so the initial amount is always the number that I'm multiplying the base by, that is to the exponent. Okay, so this number right here is going to be your initial amount. But there's nothing there. So what number could you put here to not change this expression at all? And that would be the number 1. So therefore, my initial amount is going to be 1. And then my growth factor is always the number that's the base to the exponent here. And in number 3, don't get hung up on the fact that we have an exponent of t instead of an exponent of x. The exponent doesn't really matter as long as it is a variable. That would make it an exponential function. All right, last one, number 4. My initial amount is right there, so my initial amount is going to be 5, and then my growth factor is always the base of the exponent, so my growth factor is going to be 1.02. Okay, all right, moving on to numbers 5 through 8. We're going to find the balance in each account after the given period. And if you notice, in each one of the problems, we are given a clue as to what type of formula we're going to use. And the clue is that you see the word compounded here. So what you're going to do is in numbers 5, 6, 7, and 8, you're going to be using the formula for compounded interest, and the formula that we're going to use is A is equal to P times parentheses 1 plus R to the T power. That right there is my formula whenever I have a compounded problem that involves interest. Okay, so in number 5, I am going to take the values. I have $8,000 principal. It's earning 5% compounded annually after 6 years. So I want to find the balance of how much money I'm going to have after 6 years. So I take the P. P is called the principal. The principal is the initial amount that you invest, or the initial amount that you put into the account, which is $8,000. I'm going to multiply that by 1 plus R. Now R stands for the interest rate, how much money you're earning, okay, which is 5%, but you always have to express the value of R as a decimal. So 5% as a decimal is 0.05. So I'm going to go 1 plus 0.05, and then I'm going to raise it to the power of t, and t is how much time is the given period, which in number 5 is 6 years. Okay, so then once we get to this point, I'm going to use the order of operations, and I'm going to need a calculator to calculate out the values. Okay, so the first thing I have to do is inside the parentheses, so I'm going to have to go 1 plus 0.05, and that gives me 1.05. And then I'm going to have to raise that to the exponent of 6. So raising that to the exponent of 6, I get this really long decimal. And then once I do that, I multiply that value by 8,000. So my answer to number 1 is going to be, or number 5, excuse me, is going to be 10720 point, and then since we're dealing with money, I'm always going to carry my decimal 2 numbers past the decimal. And you could round or not, it doesn't really matter. I'm not going to round, I'm just going to carry it. So $10,720.76. Okay, number 6, I'm using my compound interest formula again. My P, my principal, is 2,000. And then I'm going to multiply that by 1 plus my R, which is my interest rate as a decimal. So I have 5.4%, and moving that into a decimal, which means I actually have to take the decimal and move it 2 numbers to the left, or spaces to the left, that would give me 0.054. So I get 0.054 for my R value, and then my T value is my time period, which would be 4 years. Okay, evaluating this problem on my calculator, once again, I have to, first of all, the first thing that I'm going to do is I'm going to work out the parentheses, 1 plus 0.054. Then I have to raise that to the power of 4, and then I multiply that by times 2,000, and I get 2468.26, so $2,468.26. Number 7, my principal, I have a $500 principal earning 4% compounded quarterly after 10 years. Okay, so in this problem right here, I'm going to take my $500, which is my principal, then I'm going to multiply that by 1 plus my R value. My R value is my interest rate, but as a decimal, so 4% is 0.04 as a decimal. And then I'm going to raise that to my number of times I'm going to compound this. Now, a lot of people, the mistake that we're going to make is on this problem is we're going to multiply this to the 10th power, but since it says I'm compounded quarterly, this means quarterly means that this is happening 4 times every year. So if I want to know how much money I'm going to have after 10 years, but I compound it 4 times a year, this means I'm going to have to multiply the 10 times 4. So really my exponent's going to be 40. Okay, this one's a little bit tricky because I throw in that compounded quarterly thing, part of it. Okay, so working this out, I'm going to take, I have to do the parentheses first, so 1 plus 0.04. Then I'm going to raise it to the 10 times 4 power, which is the 40th power. So I'm going to raise that to the 40th power, and then I'm going to multiply that amount by 500. And that'll give me my money that I will have, $2,400, so $2,400.51. Number 8, $6,500 principal, earning 2.8% compounded monthly after 2 years. Okay, so when I put this into my compound interest formula, P, my principal is 6,500. Then I'm going to multiply that by 1 plus my R value, my interest rate. 2.8% would be 0.028 as a decimal. Always represent your R as a decimal, so 0.028. And then I'm going to raise that to the power of my time, which is 2 years, but then I have to multiply 2 by the fact that this problem is being compounded monthly. Now monthly means that it's being compounded 12 times a year, so I'm going to have to multiply 2 times 12. So really, I'm compounding it 24 times in my entire problem. Okay, once I do that, it's just a matter of evaluating. So the first thing that I do is I work out my parentheses, 1 plus 0.028. Then I raise that to the power of 2 times 12, which is 24. and then I multiply that value by 6,500, and that will give me the amount that I have, which is $12,610.95. Okay, so that would be number 8. Okay, number 9 and 10, we want to identify the initial amount and the decay factor in each exponential function. Okay, so in this one, once again, the initial amount is always the number that we're multiplying by. That's going to be before the base, so my initial amount is going to be 8. And then my decay factor, which I'm going to call df for decay factor, is always going to be the base of the exponent x. So my decay factor is equal to 0.8. All right, same idea, number 10. My initial amount is going to be 12. And my decay factor is going to be 0.1 in this problem right here. Okay, so we have those right there. All right, number 11 through, and this would be 14. That should be a 12. That should be a 14 right there. State whether the equation represents exponential growth, exponential decay, or neither. Okay, so in numbers 11 through 14, number 11, since my exponent is an x, that would represent an exponential problem, okay? So we know that this is exponential. Now we need to determine if it's growth or if it's decay, okay? Now, very easy way to tell if a problem is exponential growth or exponential decay. You look at the growth factor, which right here is 3. If the growth factor is more than 1, that means we have exponential growth. Okay? If the growth factor is smaller than 1, like a decimal, smaller than 1, then it'll be exponential decay. So moving on to number 12, first thing we notice is we have x as an exponent, so that makes this an exponential problem. And then we look at the growth factor, which is right there, 0.3. Now you ask yourself, is that number bigger or smaller than 1? Since that number is smaller than 1, that means we have exponential decay. All right? In number 13, first thing we do is we look at the exponent. Now, the exponent is a 2, which does not make this an exponential equation. So number 13 is neither exponential growth or exponential decay. All right, in number 14, we have y equals 0.9x. So the x is the exponent, so this is an exponential problem. And then, to determine if it's growth or decay, once again, we look at the growth factor, which in this case is 0.9. And if the growth factor is smaller than 1, 0.9 is smaller than 1, that means it's an exponential decay problem. All right? Okay, number 15. The town manager reports that revenue for a given year is $2.5 million. The budget director predicts that revenue will increase by 4% per year. If the director's prediction holds true, how much revenue will the town have available 10 years from the date of the town manager's report? Write an expression to represent the equivalent monthly increase in revenue. Okay, so in this problem right here, we are going to, the first thing we want to do is we wanted to determine, is this exponential growth or is this exponential decay? Okay, since we predict that the revenue will be increasing, we know that this is an exponential growth equation, or it's a formula we're going to use. So to write the expression, we're going to use the exponential growth expression, which is y is equal to a parentheses 1 plus b to the x power. And remember, when we fill this out, a is your initial amount, so your initial amount is 2.5 million, which would be 2,500,000. Then you're going to multiply that times 1 plus, and now b is going to be your growth percentage. Okay, so your growth percentage we can see is 4%. Now, we're not going to write, whenever we fill out the b value, we always are going to put the percent, but we're going to put the percent as a decimal. So that would be 0.04. And then to the power of, an x is going to be how many years we're going to extrapolate or predict. So we want to figure out how much revenue will the town have available in 10 years. So x would be 10. So that right there would be the expression that we could use to figure out, to estimate to how much the monthly increase will be after 10 years. Okay? Number 16, a wildlife manager determines that there are approximately 200 deer in a certain state park. The population is growing at a rate of 7% per year. How many deer will live in the park after 4 years? So here we have a growing problem, so that means that I am going to use the exponential growth equation. Y equals A times parentheses 1 plus B to the x power. Some people put this as t power for time, but I'm going to go ahead and put this as x. Okay, so putting my numbers from my problem into this formula, A stands for the initial amount. The initial amount is 200 deer. So A is going to become 200. Then I'm going to multiply this by 1 plus, and then remember B is the growth percentage. So it's whatever the problem is growing by as in the percent. And we can see the population is growing at a rate of 7%. Well, 7% is 0.07 as a decimal, and I always express this as a decimal, my growth percent, which is B, as a decimal, and X is going to be the time, okay? I'm trying to, how many deer will live in the park after 4 years. I'm trying to predict how many deer will live, okay? So once I get my expression here, I'm just going to use my calculator. I'm going to evaluate. Work out the parentheses first, so 1 plus 0.07, that gives me 1.07. Then I have to raise that value to the 4th power, which gives me that long decimal, and then I'm going to multiply that by 200. And that answer is how many deer. Now, that is just going to be 262. We're not going to consider the decimal in this case, and the reason is because we can't have a decimal of how many deer there are. So how many deer will live in the park after 4 years? We're talking about 262. Okay? In B, if the carrying capacity of this park is 350 deer, how long will it take for the deer's population to reach carrying capacity? Okay, so what this is saying is that the number of deer cannot go higher than 350 deer. Okay, so one way that I could do this problem is I could just take my expression here and I could manipulate this number 4, and I could just figure out how many deer there will be after each year. So I can kind of do this as a guess and check, where I'm always checking out my population, and I'm always comparing it to how many years that my population is going to be. So for instance, we know after 4 years I'm going to have 262 deers as a population. And what I could do is I could then figure out the 5th year and see if that is more or less than 350. Okay, so what I would do is I would use this expression here, and I would just, instead of 4, I would have a 5. Okay, so I would go 1 plus 0.07, and then I would raise that to the 5th power to see how many deer there are after 5 years, and then I would multiply that by 200. So you can see after 5 years I would have a population of 280 deer. And I could keep going and try to guess how many there are after 6 years, 7 years, 8 years, okay? So I'm going to go ahead and I'm going to jump ahead and figure out, I'm going to extrapolate, so that'd be 6, 7. Let's go ahead and figure out after 8 years how long will it take, okay? So in 8, I'm going to substitute my value here. It's going to become an 8. So I'm going to go on my calculator 1 plus 0.07. Then I'm going to raise that to the 8th power. And then I'm going to multiply that by 200. So you can see there'll be 343 deer in 8 years. Okay? So that would mean that after 8 years, I'm okay. Okay? But after 9 years, I'm not probably going to be okay, would be my guess. So I would go 1 plus 0.07. I would raise that to the 9th power. I would multiply that by 200. And you could see after 9 years, I'm going to have 367 deer in the park. So that means how long will it take for the deer population to reach carrying capacity? It'll be somewhere between 8 and 9 years. Okay, so between 8 and 9 years, we're going to reach capacity.